Hey guys, last lesson, lesson 13, second part of the linear programming. Last time we looked at the first 3 points of this lesson, and today we will talk about the second method, how to locate the optimal point. It's using the vertex testing method, and then at the end we will look at how to determine the solutions that need the integer values. Before we will move on, I will just go quickly through some of the points from last lesson, and maybe you can pause the video now and try to do these, formulate the constraints based on the sentences that are given or based on the requirements that are given here. So please formulate the constraints in terms of inequalities. Pause the video and then in few minutes play it on. If you have done it, then you could notice in the first one, or you can check the solutions. In the first one, you should have 2p less or equal to c, because as I told you last time, twice always goes with the last variable in that sentence. Because it's like if you forget the inequality, if you just read the sentence twice as many chocolates as pies, then twice goes with pies and chocolates are equal. But because we have at least at least there, then chocolates must be greater or equal to. For the second one, you should have at most 3 times. So 3 times goes with pears. And then at most, that means apples must be less or equal to 3p. The next one is twice goes with books. And computers are at least twice. That means C must be greater or equal to 2b. So the next one, you have 2 types of bookcases, X and Y, and you want at most 1/3 to be type Y. So suddenly my pattern breaks because I can't follow what I said before, but if you translate this sentence into inequality, and you simplify, you should be able to get 2y is less or equal to x. If you didn't, it's completely fine if you got this one, because this is actually the direct translation, okay? You want at most 1/3 of all, that means the sum, that's this part, to be the type y, okay? So the type y must be at most 1/3 of all. But if you simplify it, then you would get this 2y is less or equal to x. And then the last one, you have at least half as many reds as blue. That means half go with blue, and you have at least half as many reds as blue. That means red must be greater or equal to half blue. The next point, what I want to look at it quickly, just to review how to use the objective line or ruler method to locate the optimal point. If I want to maximize the 3x plus y, that's my objective function. So first you have to sketch the objective function, and then because I'm maximizing, I want to go away from the origin, and you will keep the line, or you will move the line, keeping it parallel while moving until you're not going to find out the last point of the feasible region that they will have in common. So in this case, the black dot is the point, right? Then the solution would be 20 and y, and n would be 60 as the maximized value. If you have the case of minimizing, then obviously again you sketch the line, and then you're going to move towards the origin or towards the last point of the feasible region, okay? So that means you need to find out again the point that is that the line has in common with the feasible region. There is an intersection point, and while you're moving the line, you have to keep it parallel, obviously. So in this case, this would be the point of the optimal solution. Now, we're going to look at how the vertex testing method works, because you could notice that every single time you're going to look for the optimal solutions, if you have done your problems, you could notice that it always happened to be at the vertex of the feasible region. That means this gives the way to vertex testing method, because what I need to do is basically to test or to check every single vertex and to find out which vertex gives me the largest value or which vertex gives me the smallest value. Depends if I'm maximizing or minimizing the objective function. So if you look at this example that we have done before, we used this I think last lesson. So I have 1, 2, 3, 4 vertices, and each of the coordinates are given. If they are not given, obviously you need to find it, just like with the system of equation. And then let's do the A case first. If I'm maximizing m, that means it's the sum of x plus y, x and y, then you're going to check the values of m at every single vertex. So at A it's 22.5, at B is 18, C is 15, and D is 13.5. Because you are maximizing the m, then obviously the biggest value of these all given values or found values is 22.5. So that means your solution would be x value should be 7.5, y value should be 15 if you want to maximize whether it's profit or whatever else it is, and the value of the maximized or maximized value would be 22.5 in whichever units are given. Then if you're minimizing n in such a way that the objective function is x plus 3y, then again do the same, plug the values of the coordinates of the vertex into the objective function, find the value at every single vertex, and then because I am minimizing, I'm looking for the smallest one. So in this case, the smallest or the lowest value is 27. So x is 9, y is 6, that's the optimal point or optimal solution from the feasible region, and the value of n is 27. So now please, let's try your turn how to use this vertex method. In the example 2, they are given the coordinates of the vertices of feasible region, and you need to find out the optimum point if the aim is to maximize m or maximize n later. So the points or the coordinates are given here. Well, they are not named, but you can easily find out which one. Well, A is at the origin, B is on the y-axis, E is on the x-axis, and then D and C you can easily locate. So please pause the video, try to do it. If you plug it in value by value or the point by point, vertex by vertex, then you should get these values. You can check because you have done it actually, right, with your pen in your hand. So when you go through, and because you are maximizing the m, then by inspection you can see easily that the D point is the point that will maximize the objective function m. And for the n, again plug it to the objective function, and when you do so, then you are maximizing again. That means B point is the point that will maximize the n. So then you can make the conclusion that m maximized is 760 at x equals 320 and y equals 120. And then n is maximized at value 1600 at x equals 0 and y equals 400. You can always verify with the second method that the point that you found out is correct. So this is the same problem, and we will verify it by the objective line method. If you maximize 2x plus y, so first the objective function, then move it away because I'm going away from the origin because I'm trying to maximize the objective function. Then I located the point. If I want to find out the coordinates of this point, then obviously you need to find out the solution of the system of two equations that represents the two lines that are meeting or that the point is the intersection of. Once you find it, then it's 320 and 120, which gives you the maximized value 760, what is the same as before. And then the second one, if you maximized n is x plus 4y, again, first the objective function, and once you find out the objective function, move it away from the origin, then you find out 0 and 400 are the coordinates of the point of the optimal solution, and then when you plug it in to the objective function, then you get 1600 just as before. Each of these methods, whether it's an objective line method or a vertex testing method, has its own advantages and disadvantages. Unless it's specified which method you need to use, you can choose. If the coordinates of the points or all the vertices are given, I think personally that the vertex testing method is faster, because you just plug the numbers in and find out which coordinates or which point maximize or minimize the objective function. But if they are not given and you need to find out the coordinates of every single vertex of the feasible region, I think it's much longer or takes longer time, because you need to be solving many system of equations. Again, unless it's specified which method to use, that's your call and you can decide whichever you prefer. And now the last point that we need to talk about and go through is how to find out the solution with the integer values. Because obviously, if you recall the very first problem we have done, we talked about the cow and sheep and how many cows and how many sheep we need to buy. Then this problem obviously requires the integer values for the solutions. There are two methods how to do it, and they depends on the scale of your graph. Because if you look at the example 3, you see the little feasible region there, and the task is to maximize the p x plus 2y. So when you plug or when you sketch the objective function line, and then because I'm maximizing, I'm moving away from the origin, I find out my point, optimal solution point, that is the yellow dot. And because the scale is pretty clear, I know which point will give me, or which point is the closest that has the integer values. So you just move down and you will find out that the closest point is obviously 3 and 6. However, sometimes it's not obvious which point is the closest to the intersection points of these two lines and has the integer values of the coordinates. Okay, so for example, in example 4, this is going to be the case. Again, it depends on the scale that you have. In this example, the point was to minimize the objective function of the probably cost, x plus y. And when you try to sketch the objective line, and because I am minimizing it, I'm moving it closer to the origin. And when I move it, I locate this point. And because the scale, it's not easy to say which point is the point that is the closest to the yellow point and has the integer values. And because it is not obvious which point is the closest one due to the scale, then there is a method how to find out the point which is going to be the closest to the yellow point, that means the intersection point, which will satisfy every single constraint given, that means the point will come from the feasible region, and yet will minimize the objective function. And I'm going to show you the method on the next slide, but I'm going to solve the same example, so I'll just take the picture there. Then you will find out the solution of this system of equations, the purple and blue line, and when you do that, then you discover that x and y value are not integers. This is a signal for you that the next step that you need to take is to test the 4 nearest points if the integer solution was required, right? In order to test them, first you need to locate them. So if you look at the point that you found out as the intersection, then you know which are the points that are closest to this one and has the integer coordinates. So because you have 105 point something, then it will be either 105 or 106. And then because you have 236 point something, it will be either 236 or 237. This gives you the combination for the possible coordinates, and the 4 possible points or the nearest points that you need to test. Now, what happens next, you take these 4 points and you need to verify if the point actually is in the feasible region. That means if it satisfies all the constraints that were given. So look at the first one. If you plug it in, then you find out that 997 is not greater than 1000 or not equal to 1000. That means this you don't even have, in this case, you don't even have to check the rest of the constraints because you simply know that it's not in the feasible region. That's why it's not the point you look for, because it's out. Then the next one is 105 and 237. Again, the first constraint was not satisfied. That means it's not in the region, and you don't have to do evaluate. You don't have to evaluate the objective function at all. Now, next one. If you plug 106 and 236, the first constraint is satisfied, but the second one is not. That means it's also not in the feasible region. And then the last point that you locate and you're going to test, the first constraint is satisfied, the second constraint is satisfied, that means it is in the feasible region, and then you find out the value. And this is how you locate the optimal solution and how you find out the value of the objective function. It is possible that you will have 2 points that are in the feasible region that satisfy both or all given constraints. If that's the case, then obviously you find out the value of the objective function in each case, and then you just choose the one that is either minimized or maximized, depends on what you are looking for. The second guided practice that we need to go through, I try to mix up the problems, so not all of them requires the solutions with the integer values, or in case even if it's required, then sometimes it's easier to see, so you are able to decide which method is needed. So in example 5, please pause the video, really try to do it on your own, and then you can check the solution, check the process. In case you cannot identify the mistake, in case you had some, then obviously you can contact me right away, or you can come and ask. So in this case, we have the company that produces 2 types of the wooden bedroom suites, Oxford and York, and after the pieces of wood have been cut and finished, all the materials must be packaged. The table shows the time in hours that is needed to complete each part of the process, cutting, finishing and packaging, and the time available each week is 66, 56 and 40 hours respectively. The company wishes to maximize the profit, and the first thing you need to do, or you are asked to do, is to write down the objective function. So if you carefully read the information and decode it, then you know that the objective function for the profit is 300x plus 500y that must be maximized. The second part of the question is to write down the 2 further inequalities to model the situation, in addition to the inequality 2x plus 3y is less or equals to 36. Now you may ask where that inequality comes from, but if you carefully read it again, you can decode it that for cutting I have the time available is 66, so 4x plus 6y must be less or equals to 66. Then this obviously can be simplified, divide by 2 both sides of the equation, and you have 2x 3y is less or equal to 33. Now for the finishing one, again 3.5 times x plus 4y must be less or equals to 56, because I only have 56 hours. And then for the packaging one, I have 2x plus 4y is less or equals to 40. In case of finishing, you could see that we wrote, or you can write, the equivalent with the whole numbers, because sometimes it's easier to look for the x-intercept or y-intercept. Basically it's easier to work with the whole numbers. So for the packaging one, this can be further simplified to x plus 2y is less or equal to 20. In the C case, you need to illustrate all the inequalities that you found in the B case. So take the graph paper and try to sketch it, sketch these three inequalities so you can locate the region of the feasible solutions or feasible region. When you tried, I used in the animations, I used the x and y intercept. So for the first constraint, 2x plus 3y is less or equal to 33. Then I located a point 0, 11 and 16.50. Then for the second one, I have 0, 14 and 16, 0. And for the third one, I have 0, 10 and 20, 0. This actually helps us to decide the scale that we need to use on the x-axis and y-axis. Because of the maximum value on the x-axis is 20 and maximum value on the y-axis is 14, then you can decide on the scale and then sketch each bordering line one by one. Because each constraint includes equal sign, then every single line will be solid, not dashed. And just as before, so I start with the first one, 0, 11 and 16.5 and 0. Those are my y and x intercepts for the first line. Test the origin, because origin is not part of the line. If you plug the origin, that means 0, 0, into the constraint, into the inequality, then it's satisfied. That means the side or the half plane that includes origin belongs to my region, and I will shade away the rest of it. Repeat the same for 0, 14 and 16, 0. I have my borderline and test the origin. Again, belongs there, so shade away the opposite half plane. And for the last one, 0, 10 and 20, 0. Sketch the line and again test the origin. Again, belongs there, so shade away the other half plane. And this gives you the region R that will have 1, 2, 3, 4, 5 vertices that we will check in the next slide. In this part, you need to explain how to locate the optimal point. Now you are aware of the fact that you have two methods how to do it: objective line method or vertex testing method. In each case, you need to be able to explain it either verbally or in written how to do it. So what steps would you be taking? So in first case, if you are using the objective line method, you're going to sketch the objective line or objective function using the gradient, negative gradient 6 over 10. That means 6 and 10 will be the parts of the gradient, 6 on the y-axis, 10 on the x-axis. And after that, because I am maximizing the profit, I am moving the line away from the origin until I don't meet the last point from the feasible region. That is the yellow point. Because of the scale and because I clearly see that these are already the integer solutions, the furthest point has the coordinates 6 and 7. That means I should make 6 Oxford type and 7 York type of the bedroom, whatever, in order to maximize the profit. And the maximized profit would be £5,300. If you are using the vertex testing method, you need to find out every single vertex, that means coordinates of every single vertex. In this case, it would be 0, 10, then that would yield the profit 5,000. Next one would be 16, 0, that's the red one, that would yield the profit 4,800. Next one is the yellow one, what we had before, 6 and 7, what is 5,300. And then I have the last point, the light yellow. You can obviously see that this point would not be the point with the integer value coordinates, but you can easily identify the point that is inside of the feasible region, and it's the closest one to the intersection point, and in this case it's 14 and 1. So that would yield the profit £4,700. We did not check the origin, that is 0, 0, for the obvious reason, because if you take 0, 0, you're not gonna make anything, then the profit would be 0, what would definitely not be the maximized value. In the last part, of the process, it was noticed when we adopted the optimal solution that the time needed for one of the three stages, cutting, finishing, and packaging, is less than the one that is available, which could help us to save some time because we do not need so much time as they gave us to do the process. We need to identify this stage and state by how many hours the time may be reduced. So when you look at the cutting and the line that represents this region, that's number 1, then we have finishing, that's the line number 2, and then we have packaging, that's line number 3. The yellow point that represents the optimal solution that we adopted is the intersections of the point of the line 1 and the line 3. And now when you look at the line 2, it is out, it is beyond this point. That means in here I could actually take that line, number 2, and move it closer because it would not affect anything. It would not affect the optimal solution, right? So this line I can take and move it closer to the optimal solution, to the yellow point, because the maximum time possible for finishing is not used in the optimum solution. So if I have the optimal solution 6 and 7 and I'm taking the line or the constraint for finishing, then I plug it in 3.5 times 6 plus 4 times 7 gives me 49 hours that will be required, and not 56 hours as they gave us, which will help me to save 7 hours of time. So the next problem I would like you to try, again, take the square paper and do it on the grid on your own, and then we will compare the solutions. So first go ahead and sketch the region, and when you sketch the region, then check with my solution if you got it correctly, and then we will move on to the identifying the optimal solution. If you have tried, then you should see something like this. The white region is the feasible region, and now you have two options how to identify the optimal solution. You move the objective line while keeping it parallel, and then the last point that you're going to meet from the feasible region is this blue point here. Because of the scale, you can see it's not an integer value. I mean, the coordinates are not the integers. So that tells you that you need to locate the nearest point to this blue point that has the integer coordinates. By observation, you can see when I will be moving this objective line, the purple line, the last point from the feasible region that has the integer values would be this one. And then you can read the solution easily because it's 5 and 5. So one method is to identify the vertex, then see that it doesn't have the integer values, and then to locate the nearest one. In this case, it's possible because the scale is suitable to do that. However, if you are not sure which point is really the closest one, and you want to verify, then there is the second method. The second method would be that you need to find out the intersection of the two lines. So first, find out the intersection of the line 5y minus 4x, 5y minus 4x equals 10, and the second one is 3x plus 4y equals 36. If you solve it, then the solutions you're going to get is x equals 4 and 16 over 31, and y equals 5 and 19 over 31. This gives you now the idea which point you should test, and feel free to always sketch it just to imagine, because you know that if this point is the point of intersection that you just found out, then obviously this must be point 4,5 and 5,5 and 4,6 and 5,6. So these 4 points, you need to test if it satisfies every single constraint. We had quite many constraints here, so I'll try to squeeze it here somehow. So this would be the vertex, or well, not the vertex, the point that I want to test. Then the first constraint was 3x plus 4y is less or equal 36. Lastly is y is greater or equal to 2. So the first point that I'm going to test is the point 46. When you plug it into the first one, you get 36 is less than 36, what is okay. Next one is you will get 406 is less than 117, then it's also satisfied. Next one is 14 less or equal to 10. So in here it breaks and you don't have to follow this point anymore because it's not in the region. So I can just skip this point. Next one is 4 and 5. 4 and 5, if you plug it in, then you will get 32 less or equal 36. Next one, if I'm not mistaken, you should get 97 less or equal 117. Next one, you will get 9 is less or equal to 10. Next one is 49 greater or equals to 30. And obviously 5 is greater or equal to 2. So this point is the potential point because it lies in the feasible region. So it's possible that it might be the closest to the intersection point. Next one is the point 5,6. 5,6, when you plug it into the first constraint, you will get 39 is less or equal to 36, what is obviously not true, so you can immediately skip this. And then the last point is the point that we located before, and we know that it will be the solution, but if I'm following this method from the beginning, I wouldn't know. So in this case, I would have 35 is less than 36, then 110 is less than 117, what is satisfying, then 5 is less or equal to 10, 55 is greater or equals to 30, and then last one is 5 is greater or equal to 2. So this point is also okay. So I have this point to choose from or this point to choose from. If the scale allows you, like in this case, what we could do, well, obviously I didn't even have to try some of the points like 4 and 6, because when you look at the picture, 4 and 6 is here, what is obviously outside of the region, right? And the next one is 5 and 6, that is this one. That is also obviously outside of the feasible region. However, it is not always possible to see this clearly due to the scale, and you need to show that you have tested the coordinates of every single point for every single constraint, or you would have to explain it like what I just did now, but you would have to do it in written, that I checked point 4 and 6 based on the graph, it's obviously outside of the region. That is why I didn't have to change, or I didn't have to check it for every single constraint. Now I have my two candidates, and that's point 4 and 5 and 5 and 5. So point 4, 5, I'm going to check the objective function, that is p 4 and 5 is 4 plus 2 times 5, what gives me 14. And then second one is p at 5 and 5, what gives me 5 plus 2 times 5, what is 15. Obviously, because I'm maximizing it, then this one, 15, is bigger than 14. That's why the optimal solution would be 0.55, or optimal point would be 5,5, which would bring me profit of 15. Profit maximized is 15. And finally, one last problem that will go back to section 1. That's the formulating the problem, how to rewrite the problem into the linear programming. Manager wishes to purchase seats for a new cinema. He wishes to buy 3 types of seats: standard, deluxe, majestic. Let the number of standard, deluxe, and majestics to be X, Y, and Z respectively. Standard, Deluxe and Majestic seat each cost 20, 26 and 36 respectively, and the manager wishes to minimize the total cost, obviously. Formulate the situation as a linear programming problem, simplifying your inequalities so that all coefficients are integers. So now the constraints that he gives us are these ones in these boxes. Please, now is the time for you to stop the video and try to do it on your own and then check if you got it correctly. In case you are unsure or you cannot clarify it with my solution in the video, then write me or come to ask. So he decides that the total number of Deluxe and Majestic seats should be at most half of the number of the standard seats, which, if you wrote it, gives you that y plus z must be less or equal to x over 2, because the sum of them must be at most half of the standard seats, what is the x. When you simplify it, because the requirement was to write the constraints with the coefficients that are integers, then you will get 2y plus 2z is less or equals to x. The second one, the number of the Deluxe seats should be at least 10% and at most 20% of the total number of the seats. So that's the ratio, right? If you have a total number of the seats, it's x plus y plus z, and the part that the Deluxe seats will make out of the total is obviously the fraction y over the total, and must be at least 10% and at most 20%. So there will be the second one here. And when you simplify this, then you should get 9y is greater or equal to x plus z, and 4y is less or equals to x plus z. Then the next constraint that is given is the number of Majestic seats should be at least half of the number of the Deluxe seats. So this is quite easy, because z must be greater or equal to half of y, because it must be at least half of it. This can be simplified to 2z is greater or equal to y, so we satisfy the integer coefficients condition. Then the last one is the easiest one, because their sum must be greater or equals to 250. Now, non-negativity, obviously you cannot buy the seats that are negative in numbers, so x and y and z, all of them must be greater or equal to 0. Objective function, what he wants to do is to minimize the cost, because you know how much is each of the seats, then 20 times x, 26 times y and 36 times z, the sum of this is the cost that you want to minimize. And this is the whole problem. And now finally, the last self-practice. I have chosen a couple of the problems from set 6c and 6d, which you can do either before the tutorial or after the tutorial during the week. If you struggle, the answers are at the back of the book. The detailed solutions are on this website. And obviously you have me either online or in person. I will see you in the tutorial. We will conclude it, and then we will move on to the practicing the released problems. Bye guys. Ciao.